So to start with in Lab 4, you're going to look at 4 simulations. So as usual, you go to the 1100 folder, and you look for the folder that says Lab 4, open that up, and you'll find 4 simulations in there. So I'll open up the first one. So what'll happen here is I'll click Run, and it's going to show me a little movie of a ball on a string moving in a circle. So I'll run that. And the program keeps track of what's happening with the x and y components of the velocity and also the magnitude of the velocity. So you can see how those change or don't change in time. And they ask you a few questions about this. So they say what's happening to the velocity components and what's happening to the magnitude of the velocity, the speed. Also, what's happening to the velocity vector, so that arrow that is attached to the speed. And then finally, the last question is probably the most important. Why is it that we say that this object is accelerating? Because I can stop the motion at any point, and you can see that the speed is 2 meters per second. So I can run it and stop it absolutely anywhere, and the speed is always 2 meters per second. So given that this object has a constant speed, why do we say that it's accelerating? Hint, hint, I said speed, not velocity. Think about that. So once you've answered the questions, you can go on to the next simulation. This one is going to be, again, a ball moving in a circle. The program fills in the velocity vector. As soon as I click Run, it's also going to fill in the acceleration vector. So I'll show you that. So in this case, you're looking at those 2 arrows and watching how they change over time. And there's questions on this as well. The question they ask you in question 2 is, in what direction is the velocity vector pointing, and in what direction is the acceleration vector pointing? So they mean relative to the circle, because obviously they're changing the direction over time. And in your manual, there's a sketch there. That's basically a snapshot in time of this motion, and they want you to draw in what direction the velocity and the acceleration vectors are pointed at that moment. They also want you to describe what direction they're pointed relative to the circle. So it might be useful to use phrases like tangent to the circle or towards the center. So you fill those in. And then question 3 is not actually a simulation at all. So I'm going to show you a bit of different video to explain how to do question 3, and then I'll come back and show you how to do the next 2 simulations. So question 3 is asking you to do a vector subtraction, but it specifically wants you to do a graphical vector subtraction. Not everybody's instructor actually shows them how to do this in class, so I'm just going to show you here so that you can do question 3. So this is the diagram that you've got in your book, and it's basically showing an object at 2 different times and the velocity vector at those 2 different times. So when the object was here, the velocity vector pointed like so. When the object was over here, the velocity vector pointed like so. So it changed its direction over time. So to do a graphical subtraction, what you'd need to do is, you'll have to do this by hand with a ruler and maybe a protractor if you've got one, is you take this first vector and draw it over here so that it's touching tip to tip with this other one. So I can do that very easily with the computer. I just take a clone and move it over here so it's tip to tip. Now, because this is actually supposed to be a vector subtraction, if you were doing this correctly, you would swap the direction of the arrow. So this second one would actually point back this way. But in general, what you're doing is you're going to take this first arrow and with your ruler very carefully draw it over here, same angle, same length, but touching tip to tip with this other vector. And once you've got that, then the subtraction, one minus the other, of those vectors would be the vector that connects the 2. So this red one here. And if you do it carefully, it should point towards the center, which is what we expect in uniform circular acceleration. So now you're ready to look at simulation 3 and 4, and we'll open that up. And what this is going to be is, again, balls traveling in a circle, but there's 2 of them. And you'll notice that the radius of rotation is exactly the same for these 2, but the speed is different by a factor of 2. So this will have a speed of 2 meters per second, and this will have a speed of 4 meters per second. Now, like before, when I click Run, it's going to immediately draw in the acceleration vector. And that's what we want to look at for this question, because you're going to be looking at the magnitude of the acceleration vectors and seeing how it affects things when you double the speed. So I'll click Run. And it immediately draws in the arrows, and you can see this one is quite a short arrow, this is quite a large arrow. look at the numbers, the actual values, and the question that it gets asked is, what happens to the magnitude of the acceleration when you double the speed but keep the radius the same? Look for obvious proportionality. So you look at those two numbers and you say to yourself, okay, is it twice as big? Is it half as big? Is it 4 times as big? Figure out what the proportionality is. So we doubled the speed. What happened to the acceleration? Next it asks, does the acceleration vary directly or inversely with speed? And I'll warn you that as worded, that's a bit of a trick question. So maybe go back and look at what the equation is supposed to be in your pre-lab and then figure out what the trick is. So is acceleration, does it vary directly or inversely with speed? And there's a bit of a subtlety there that you might miss. The last one is, based on the simulation, suggest an equation or proportionality statement that relates acceleration to speed. So what you would do is you'd write A for acceleration is proportional to, and then you write some function of speed. Once you've finished answering those questions, you can go on to the next simulation, which looks quite similar to this one. So simulation 4. In this case, again, we've got two balls that are going to go in circles. They both have the same speed, however. They're both at 2 meters per second for their speed, but the radius of rotation has been halved for this second one. So again, we're going to click run and we're going to look at the magnitude of the acceleration. We want to see if there's a rough proportionality, if something changes in an obvious way when you half the radius. So we click run and immediately you can see the two acceleration vectors. Look at those numbers, and again, you want to look for rough proportionality. So is it twice as big? Is it half as big? Is it 4 times as big? What happened here? You halved the radius. What happened to the acceleration? And again, they ask, does the acceleration vary directly or inversely with the radius? And suggest a proportionality statement that relates acceleration to radius. So again, A is proportional to some function of radius. And then question 6 says, suggest an equation relating acceleration to speed and radius. Hint, hint, that will look suspiciously like something you saw in the pre-lab or even in class. And then using algebra, you check that the units actually work out to be meters per second squared. So this is the apparatus that we use. We've got a platform that spins, and mounted on the top of that is a sensor that is going to directly measure the acceleration felt by a little figurine that's been taped to the top of the sensor. We've also got a counterweight over here just to make sure everything spins evenly, and there is a photo gate here that has been mounted in such a way that when the sensor swings by, it blocks the photo gate, and then when it swings by a second time, it blocks it again. We're going to use this to help measure the period of rotation, which is the time for one complete spin. There are 3 things you're going to need to measure using this apparatus. The first 2 are used to get a theoretical value for the acceleration felt by the figurine, and the third one is a measured value from the sensor and using a computer program that I'm going to show you later. So the first 2 things you measure are the radius of rotation and the period of rotation. So radius of rotation is defined as being from the center of rotation, so the center of this little post you see in the middle, over to the location of the figurine. And so you just take a ruler and measure that directly. Now, what we're actually measuring with the sensor, of course, is not the acceleration felt by the figurine so much as the acceleration felt by the sensor itself. The technicians don't always put out these little figurines, so if your sensor doesn't happen to have one, look on the top of the sensor box. There's a little dot there with a Z beside it, and that marks the internal location of the sensor. So your radius of rotation should be from the center of this post over to that little dot with a Z beside it, or the figurine if you have one. The second thing that you're going to measure, as I said, is the period of rotation, and we've got this timer box. It's set in pulse mode, read, which just means the little red light should be on, and there's a reset button if you need to re-zero it. So in this pulse mode, what's going to happen is that when the sensor comes by and blocks the photo gate the first time, it turns on the timer. And when it comes by and blocks it again, it turns off the timer. So we can just spin the platform, hit reset, and the timer will turn itself on and off automatically, and it'll time one complete spin. And that's what we want, our period of rotation. As I said, the third thing you're going to measure is the acceleration felt by the sensor, and you get that off of the computer screen in conjunction with a program I'm going to show you. There is one subtlety of the data taking you have to be aware of, however, and that is that when we spin this, it's actually slowing down gently due to friction. It mostly spins at a constant rate, but it is gently slowing down, and you'll actually see that on screen. So the program will show you your acceleration value, and as the data comes across the screen, you'll realize that it's a downward slope, a very gentle one. And that's just because as this platter slows down, the acceleration being measured by the sensor is gradually getting weaker. So that means we have to be careful about when we time our period and when we take our acceleration value. They have to be done at the same time, or we won't get good agreement between our theoretical acceleration value and our measured acceleration value from the sensor. So the way in which you take the data is you would give your platter a bit of a spin, you reach over and start your program running, taking data, and you watch the data coming across the screen. Now that graph has vertical lines on it, and you pick one of those and use it as a marker. And when your data reaches that marker line, that vertical line, you want to reach over and push your reset button quickly. And the reason why is then you can highlight just a small amount of data right after that marker line and get your acceleration value from that, and then that should be in good agreement with the calculated acceleration value you're going to get using this period value that you have. So before you take data, there's something that you have to do that's quite important, is you've been given a little spirit level and you need to level the apparatus. So you put the spirit level here on the platform's base, so not on the spinning part, but on the base of it. And you want to look straight down on the top of it. So put your head right over top of it, look straight down, make sure that the bubble is centered within the circle. If it's not, then the ends of these little legs can be twisted to raise and lower the different parts of the apparatus. So you can use those little legs to level things carefully. And you want to do that because if you don't, then when you look at your data coming across the screen, you will see a wavy line. So if things aren't leveled, you see that wavy line. A little bit of a wiggle's not a problem, but ideally, if everything's leveled properly, you should see a completely straight line come across your screen. Alright, so this is the program that you're going to use for the spinning platter to find the acceleration on a spinning object. And you go in here to the 1100 folder, and there's two circular acceleration programs. We specifically want the one that says CMBL. There's also a Data Studio version. We want this one, CMBL, Circular Acceleration. So we open that up, and because there is a wireless sensor and we need to get it talking to the computer, we first need to set things up. So first of all, make sure that your sensor is turned on. So make sure it's lit up and turned on, and then you go up here to Experiment, Connect Interface, Wireless, and then Scan for Wireless Devices. You may need to do this a couple of different times because sometimes it doesn't always find yours. So you wait, and if there's a list of them, just be careful. Look at the name on the side of your sensor and make sure you've selected the one that's yours, not your neighbor's. You hit OK. It'll give you a collect button up here. Before you do anything though, you want to zero the sensor. So the way to do that is without the platter spinning at all, just click this 0 and then say OK to all the defaults. So the important thing is that your sensor is not moving when you do this. So now we should be ready to take data. So what I do is I give the platter a nice spin. Faster is slightly better, and then I hit collect, and you should see data coming across the screen. The data will look like a straight line if you've leveled your platter properly. If not, then you would see a wiggly line on here. So this is a nice straight line. The important thing I would do if I was taking data is when I'd spin it, when the data is coming across the screen, at a certain point I have to hit the reset button on my photo gate to make sure that the acceleration value I'm getting corresponds to the period that I measure with the photo gate. So say I hit the reset button when the data got to this point. So it's progressing across and I hit the reset button here and then it keeps going. If that were the case, then I would want to highlight just 1 second's worth of data right after that point. So I hit the reset button right here and then I select 1 second's of data right after that. And then to get my mean acceleration, my average, I go Analyze here at the top and then Statistics. And that gives me a box that contains the mean value, and this would be my acceleration value. And it's going to be measured in meters per second squared.